Alright, so we're back. And I think the audio should be fine. Okay, so we're going to go ahead and move into the next section. So we're moving into chapter 4. So that was all that we wanted to do from chapter 3. We're going to go ahead and move into chapter 4 with inverse, exponential, and log functions. Okay, and we're going to start with section 4.1, inverse functions. Okay, so let's see. So suppose we define this function that you see here in red and blue. We can form another set of order pairs by switching the x and y values, and we call it g, right? So we have the red and blue for f, and then for g we just switch the x and y coordinates, so we switch them around. So to show that these two sets are related, g is called the inverse of f. For a function f to have an inverse, it must be a one-to-one function. A one-to-one function, in a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value, right? That should be working. Yeah. Okay. Let me see. So what this is called a correspondence diagram. With the correspondence diagram, again, for it to be a function, you can't have one x going to two different y's. And so that's basically, in a function sense, that's passing the vertical line test. For the function to be one-to-one, it has to pass the horizontal line test. What that means is you can't have one y value going to two different x values, right? So notice we have the y value of 7 that has two different x values going to it. I'll call that a merge. Whenever we have this merge thing going on, then that means that the function is not one-to-one. That means that it does not have an inverse. Okay. So notice that every y corresponds to exactly one x. Every x corresponds to exactly one y. If we were to plot these points, it would pass the horizontal line test. So function is one-to-one. Whenever a is not equal to b, this implies that f of a is not equal to f of b. That is, different values of the domain correspond to different values of the range, right? So, the order pairs are unique in a sense. Using the concept of the contrapositive form from the study of logic, the last line of the preceding box is equivalent to, given that two y values are equal, it implies that the two x values are equal, right? So we can use this technique to determine whether or not a function is one-to-one, right? So we're asked to decide whether this function is one-to-one. So what we want to do, something like the following. So whenever we have f of a is equal to f of b, then if we can show that a equals b, then we say the function is one-to-one. If not, then it's not one-to-one, right? So that means if we did -4 times a plus 12 would be equal, if we said that equal to -4 times b plus 12, right? Notice we could subtract 12 from both sides. So if we subtract 12, we get -4a equals -4b. Divide both sides by -4, and then we get a equals b. So because of this, we say that each y corresponds to exactly one x. It will pass the horizontal line test, so then this function would be yes, one-to-one. All right, I'm gonna clear this out. So I think they're doing essentially the same thing we just did. Let's see another one. Decide whether this function is one-to-one. Let's try the same thing and see what happens. So let's do f of a equal to f of b. Right? Let's see if we finish with a equals b, then it is. If not, then we say that it's not. So then we're going to say 25 minus a squared equals 25 minus b squared. All right. Okay, so yeah, we should be able to square both sides, right? We can square both sides. We'll get 25 minus a squared equals 25 minus b squared. We can subtract 25 from both sides. We get negative a squared equals negative b squared. Multiply both sides by negative. A squared equals b squared. Now when we go to take the square root on both sides, we get plus or minus the square root of a equals plus or minus the square root of b. So what this is saying is that the square root of a, sorry, that's not right. Let's go like, okay, I can fix it. So let's just do it like this. Squared, right? So then, let's erase. Don't want to do that. Okay, anyway. So then we get plus or minus a equals plus or minus b, right? So this is saying that positive a equals positive b and negative a equals, sorry, hey, I'm just, anyway, this still works too. I'm kind of making my mistakes left and right. I'm kind of tired. So now we have one y value going to two different x's. So then it fails a horizontal line test. So then this function is not one-to-one. Not one-to-one. All right. So let me clear this out. And let's look at it. So notice when if we let x be 3 and if b is negative 3, but they both equal positive 4, right? So, you know, we have two different x values going to the same y. It essentially fails a horizontal line test, so it's not one-to-one. Okay. Okay. So another way to show that a function is one-to-one, again, do the horizontal line test. A horizontal line test means no matter where we draw a horizontal line through our graph, it touches it once. But you see in this example, we can draw a horizontal line, it touches it more than once. So this is an example of it failing the horizontal line test. So this is an example of a function that is not one-to-one. So not being one-to-one means it does not have an inverse. So a function is one-to-one if every horizontal line intersects the graph of the function at most once. Okay. So notice here we can draw a horizontal line. It touches it more than once. So this is not one-to-one. Notice with this diagonal line, no matter where we put a horizontal line, it touches it once. So this one we would say is one-to-one. Okay, I'm gonna let that be. All right, let's just kind of see this. So we're asked to consider these functions. All right, so we have f and g. Let's choose an arbitrary element from the domain of f, say 10. So when we plug in x as 10, we get what, 85? So now let's see if we take that 85. Let's take that 85 and plug it into g. If we plug the 85 and plug it into g, we should get 10, right? Yeah, we get 10. So starting with 10, we applied the function f and then applied the function g to the result, which returns the number 10. So these functions contain inverse operations that undo each other. So a function composes inverse, they essentially cancel each other out, or what was the word I was about to say? They undo each other essentially, right? So that's a function with its inverse, composes inverse. So just a few more examples of doing the same thing. They kind of undo each other. So for any value of x, whenever we do f compose g, whenever we say f compose g equals x and g compose f equals x, then we say that these two functions are inverses of each other. So this is one way that we verify that two functions are inverses of each other. I'm gonna let that be. I'm not gonna worry about that. The chat window should be working. Yeah, I just stopped it. I didn't check anything. Okay, let's keep going. Okay, so we're asked, is g the inverse of f? Let me see where they're going with this one. So we have x cubed minus 1. Notice no matter where we draw a horizontal line, it'll touch the graph y. So it looks like it's close kind of in the middle, but you kind of have to know that the function x cubed here, it still has a slight gradient. Even if you were to zoom in there, it still has a slight gradient, a slight incline, so it would still pass the horizontal line test. You can also do the f of a equal to f of b and show that a equals b uniquely. But this function does pass the horizontal line test, so it does have an inverse. So if it does have an inverse, we could talk about how to find the inverse of a function algebraically. Let's actually go ahead and do that here. So if we have this f of x equals x cubed minus 1, we want to find the inverse of this function. We're going to do the following. We write f of x as y. Switch the x and y, so these are going to switch places. So we're going to say x equals y cubed minus 1, and then solve for y. So if we add 1 to both sides, we'll get y cubed equals x plus 1, and then take the cube root on both sides. So then y equals the cube root of x plus 1. Boom. And that's where that comes from. So then we say f inverse cube root x plus 1. Okay. All right. So I'm going to clear this out and see how they did it. Oh yeah. So they did f of g of x, and they're going to show that we finish with x, and then the reverse also works. So if you did it in reverse, the same thing happens, right? So that's how we verify that two functions are inverses of each other. We do the first compose the second, if we get x, and the second compose the first, we also get x. Then that means that the two functions are inverses of each other. So f inverse, right? Okay. So find the inverse of each function that is 1 to 1. We don't have what, two different x's going to the same y, so that we have a repeating y's. We do have a repeating y. So the negative 2, 1. So this does not pass the horizontal line test. So it does not have an inverse. We have no repeating y's. 1, 2, 3, 0. No repeating x's, no repeating x's, right? So the inverse, you just switch the x and the y. So notice all the x and the y's just switch places in this case. Any repeating y's. So no repeating y's here, so it should have an inverse function. You just switch the two columns. Yeah, we just switched everything, right? That's the inverse function, okay. Oh, wow, this goes on for a while. Okay, so we actually just did this. So we'll do another quick demo on finding the inverse function here. So to find it again, we replace, decide whether the equation, first we actually decide whether it defines a one-to-one function. So let's just quickly do f of a equal to f of b, right? So then if we say 2a plus 5 equal to 2b plus 5, subtract 5 from both sides, we get 2a equals 2b. Divide both sides by 2, a equals b. So then that means that the function is one-to-one. So then we're asked to find the inverse equation. So if this is the original, we switch the f of x with y. So we're going to say, we replace f of x with y, y equals 2x plus 5. Now we switch the x and y. So then we get x equals 2y plus 5. And then we solve for y. So that means 2y equals x minus 5. Y equals x minus 5 divided by 2. So then this is going to be the equation of our inverse function. Okay. Alright, I'm going to clear this out. So they looked at the graph and they saw that the graph has the horizontal line test, so it does have an inverse function. So they switched the x and the y, solve for y, and then that's our inverse function. So no, this is a graph of a quadratic parabola. It's a U-shaped graph. So it's going to fail the horizontal line test, so it's not going to have an inverse function. So it's not one-to-one, it does not have an inverse. So the plus or minus, right? There are two y values for each choice. So yeah, it's not one-to-one. So notice that this is the graph. No matter where we put a horizontal line, it passes the horizontal line test. Oh, let's go ahead. Well, yeah, we can go ahead and find the inverse, right? So if we have y equals x minus 2 cubed, we switch the x and the y. So then we say x equals y minus 2 cubed. Solve for y. So take the cube root on both sides. So then y minus 2 equals the cube root of x, right? So because it's an odd index, we don't need the plus or minus. We only need the plus or minus when we're doing an even root. And if we add 2, so then y equals cube root of x plus 2. So then f inverse cube root of x plus 2. Okay. Okay. Let's see what we got going. Let's keep it going. We got 64. So we're given that this one is one-to-one. We're told to just find the inverse. Okay, so let's find the inverse here. Actually, I think I'm going to give myself some space for this one. So I'm going to open this up over here. All right, yeah, I'm definitely going to have to stop after this one. I can feel myself. I'm barely hanging on energetically. Let's crop. I'm going to put that there. Okay. So let's get a copy of the original. We have this, and let's actually go like this. So we have this f of x equals 2x plus 3, x minus 4. We should identify the domain and range. Notice that the domain of this, it says that x is not 4. I'm just going to tell you for now that the range is y is not 0. Right. The horizontal asymptote. Negative 2 by 3, right? Sorry, 3 by 2. It might cross the horizontal asymptote because sometimes you actually can't cross it. Let me think about it. Y equals 0. Well, so it might be all rails. Because there is a horizontal asymptote, but it's actually touching the horizontal asymptote. You can touch the horizontal, but not the vertical. So I'm going to remove this. I think the domain, I think the range might be all rails. We're going to let that be for right now. Okay. Oh, so we find an inverse here. So then we say y equals 2x plus 3, x minus 4. So let's switch the x and the y. So we're going to say x equals 2y plus 3 over y minus 4. Let's solve for y. I'm going to multiply both sides by the denominator. We're going to get xy minus 4x equals 2y plus 3. So then let's get the y terms together and everything else on the other side. So then we get xy minus 2y equals 4x plus 3. Factor out the y. So we say y times x minus 2 equals 4x plus 3. So then y is going to be equal to this 4x plus 3 over x minus 2. So then we say f inverse 4x plus 3, x minus 2. Okay. Find the inverse. So we got 4x plus 3 divided by x minus 2. Let's go back and see how do we do. Nope. Anyway, let's see how do we do. Okay, that's fine. I think that's what we got, right? Okay. So we get the condition that x is not 2. Note that 2 was not in the range of f, so it is not in the domain. 2 is not the range. Oh. The horizontal, yeah, I was doing that wrong. Okay, so the horizontal asymptote is y equals 2. We'll talk about that. We haven't gotten there yet. Well, maybe not, but so there's a test for horizontal asymptotes. If you look at the exponents, like one of them is to the power, they both have the same exponent. So then it's a ratio of the leading coefficient. So then y equals 2 was the horizontal asymptote there. So then, yeah, that's why we had to throw out the 2 there. It's these 3 tests that kind of go together when we talk about rational functions. In a graphical sense, the original function with its inverse is going to rotate about the line y equals x. Because remember, we're taking, like when we have a function, it's all these ordered pairs, all these x comma y's. When we look at the inverse, we're switching the x comma y, so they all switch over this line y equals x, right? And so instead of, whenever we have a comma b, then the inverse is going to have b comma a. It's like a mirror image across the line y equals x. I'm gonna let this be. So, okay. So notice this says we're given this f and we're asked to find f inverse. Notice for the square root function, all the manipulations are inside, so these are all horizontal manipulations. So notice we didn't move it up or down, so we can go ahead and identify the range. We can say that the range is what y has to be greater than or equal to 0, right? So that'll come in handy when we go to find the inverse. So let's find the inverse. We're going to say y equals the square root x plus 5. So switch the x and y. So x equals the square root of y plus 5. If we solve for y, square both sides. So then we say y plus 5 equals x squared. Subtract 5, y equals x squared minus 5. So what should be the case, so then f inverse is going to be x squared minus 5. So now our domain, so it should be the case that x has to be greater than or equal to 0, and y has to be greater than or equal to -5. I think that's how that goes. Yes. All right. So basically, the domain and range just switch, right? So I'm going to clear this out. Yeah. So that's what we did. Okay. I think that's about it. You can go through this on your own. Oh, yeah. I do. Okay, I'm gonna leave a coded message. Hmm. I don't have one ready to go. Mm. So I'm gonna let you go through this on your own. What it is it's a given a function. Uh, you can use this inverse. You can code the message and uncode it using the original function and its inverse. If you take those results and feed them, just kind of go through this example. You can kind of get it on your own. I do intend on making a code and probably leaving it in the description here. I'm trying to think how I want to offer the extra credit though. If you remind me in class, just remind me in class and we'll do it that way. Because I know right now I'm about to turn this off. I'm about to close my eyes. I'm totally about to pass out. But yeah, I want to make a coded message, and if you go through this example, instead of be my Facebook friend, I'm gonna like make a different code or whatever. And then if you're able to decode it, you know. So like this, what you see here would be the code for that message, and then if you put it right, so that if you put those results into the inverse, so then use the inverse function to decode it, you would take those results and put it into the inverse to decode the message. All right. So make one for you all. Okay. So on that note, we will end the session here. So at least we got at least 2 sections. We did full lectures. We went on and did 3-1 and 4-1. I do want to go ahead and make video lectures for the rest of them so we can just have them on file. For 4-2, 4-3, and 5-1 will be the last of the material. Okay. So we're going to end the session here. This is just something here for your viewing pleasure, because I know that some of my students have actually been using those videos, and so that we can kind of keep it moving. So there are 3 more that we need to do. We'll get those going, but we'll end the session here. And from one beautiful mind to another, enjoy the rest of your evening.